Here I am again sitting in the lobby of Capital Christian School talking to you about chi-squared test. I know we're not to that point yet, but this is the introduction to this next chapter. And what we're looking at is categorical data. So we've been doing so much with quantitative variables, and looking at all the different tests that we can run, but we've not had a chance to talk about what happens when you're dealing with qualitative variables or categorical variables. And because, I like food, this is M&Ms. All right, M&Ms, and we took a packet of M&Ms, and there were a total of 60 of them in there, and we counted how many we had of each. Now, if you go to the website, you can actually find out the true proportion of what they say should be in every bag. So I'm going to put that on here for you now. So those are the proportions of what they're supposed to be. So you can see blue is supposed to be 24%. And what we're going to do when we're doing tests like this is we're going to be checking to see is what we have consistent with either what it's supposed to be or what's expected in some kind of level. So in this case, we're going to see is the count that we're seeing here a good fit for what it's supposed to be. So in order to do that, I need to take this 60 and multiply it by every one of those values. All right, so if I do that, I will get an expected count of 14.4 for blue. So that's 0.24 times 60. I'm going to have 12 here. I'm going to have 9.6, 8.4. Reds should be 7.8. And then browns will also be 7.8 because they're both 13%. So then what we're going to do is there is a formula that we're going to use to find a test statistic, all right, but we have to start with the conditions. We have to assume that this is a random sample of M&Ms, and that selecting them there will be over 10 times the amount in the population, so very similar to what we did before. We'll go into that a little bit in detail later. I'm just going to show you the quick formula for how to do this. So it's called chi-squared. Chi is the Greek letter, like that. So it's called chi-squared test. And the chi-squared test has a formula. Chi-squared itself is equal to the sum of, so capital sigma, the sum of, we're going to add a whole bunch of things up, observed minus expected squared divided by expected. And that's going to equal, so if I take each one of those, let's go to this color again. If I take each of those, so let's take the first observed, and that's blue, and that's 9. We're going to subtract the expected, which is 14.4, square it, divide by 14.4, plus, then you do the next one, 8, which is the observed for orange, minus 12, squared, divided by 12, the expected, plus dot, 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 and you go to the last one. That's 6 for brown minus 7.8 squared divided by 7.8. And I will get a chi-squared value of 10.180, which means nothing to you. If you've been remembering, so this is my chi-squared value. Chi-squared is equal to 10.180. In doing a t-test or a z-test, this would seem like a crazy huge number. In a chi-squared, it's not so much. So again, degrees of freedom here, much like the t, is going to equal number of categories minus 1. So we had each color as a category. So blue, orange, green, yellow, red, and brown, that's 6 categories. So my degrees of freedom is 5. A chi-squared distribution is a right-skewed distribution. I have this value here, 10.180. And if I look to my chi-squared, your packet here, we've done the z, we've done the t, and the last one on the back page is chi-squared. And I look to the 6 degrees of freedom row, and I go across. I find that 10.1 is in between 15 and 10%. So this is it's somewhere between 10 and 15%, which is not significant. Our significance still stays the same as like 5%. So what we saw would happen somewhere between 10 and 15% of the time, which is not unusual. So there is no good reason to suggest that my this one sample that I did, there's no reason to think that this sample is any different than what it is supposed to be, which would be that, on average. You can't actually have a decimal place of an M&M when you're counting whole M&Ms. So this is the idea behind a chi-squared test, getting you introduced to the idea that a categorical variable can, in this case, have a good fit. So this is what's called a goodness of fit test. I'm not going to get hung up on the names because they're all essentially the same concept that we work through when we're doing it. So it's a goodness of fit test. So now that we've done one, we're going to jump back to the beginning. My null hypothesis is that, in this case, proportion of M&Ms is what they claim. My alternative is that the proportions are different. Okay, you'll notice what changes here is in our null and alternative hypotheses is that we're no longer using symbols. I could put all of them in there, that P of brown does not equal point whatever it was, and the P of orange and the P of yellow, so that altogether the differences that we see are not due to chance. But you can get by with just using the words and writing down sentences. All right, my conditions are random. It needs to be a random data coming from a random sample or a randomized experiment. It could be a randomized experiment. Large sample. That is, now here when we say large sample is that, and this is different, all expected counts are at least 5. So the expected counts all have to be at least 5. And then lastly is independent, which is the 10% rule. Individual observations are independent of each other, and that when sampling without replacement, that is, I'm taking things out, we have to check to see that my population is at least 10 times my sample size, which was true. I mean, there's going to be well over 600 M&Ms in the whole population of M&Ms. For all you know, there's over 600 M&Ms inside of me right now. So these are the only 3 conditions that you have to do when doing a chi-squared. When we get to another section, and we're going to actually advance this, we're going to have, instead of just one row of data, we're going to have multiple rows of data. Maybe we have 3 levels here, and maybe we have 5 here. My conditions change a little bit, but we still go with, we need expected counts to be a certain level. We still need independence and randomness. For reflection response, I want you to identify what is the key difference. When you're thinking about how would you decide if you're going to be doing, let's say, a chi-square test versus one of the other tests that we've done. What, when you read, is going to be a tip-off to you? Think about that a little bit. I gave you a hint at that earlier in the video. See you in class.